So today we will talk about non-parametric statistics, something that has not been discussed yet, but something that is applicable in many practical applications. So what do we know so far from the second part of this course, especially? We have covered several statistical tests for different practical applications. So we know how to test equality of two population means with the help of T and Z test. We know how to test the equality of two population proportions with the help of Z test. We know how to test the equality of more than two population means. When we have 3, 4, 5 groups, we applied ANOVA, one-way ANOVA if there is only one categorical variable, or two-way layout if there are two categorical variables that divide these groups. We also know how to test the equality of variances in populations with the help of F-test, and if the sample is taken from a particular distribution with the help of chi-square test, and how to test the independence of two categorical variables also with the help of chi-square test. So we know a lot at the moment, and we are able to solve many practical tasks, and with the help of data we are able to answer many questions if there is a significant difference between the population parameters in two samples, in two or more samples. The thing is that almost everywhere when we spoke about these tests, we assumed the normal distribution of the data. If you remember, when we started talking about T statistic, Z statistic, or even F statistic, we assumed the normality of data initially, that the sample is taken from the normal distribution, blah, 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 and so on. Sometimes we were able to approximate in large samples the distributions, and we claim that using central limit theorem they are approximately normal. But it doesn't work all the time. For example, in F-test it doesn't work. Large sample F-test, so it doesn't have a normal distribution. And also in other cases, for example in chi-square test, we are not able to apply this test if the assumption of normality fails. And yes, so this is the question. So what if this assumption fails? And what if we have some specific cases when the variables are not kind of usual in the sense that we have discussed before? So in all these cases, we have a need for non-parametric statistics. So I will give you two examples when non-parametric statistics are essential. So one case when we have something which is called ordered measures. So what does it mean? In some experiments, the results are hard to quantify. So the result of the experiment or the result of our observation is difficult to present as a number. For example, if we ask customers about their satisfaction with our services, and we can get some grade, very good, good, moderate, bad, very bad, then we can assign some number like 5, 4, 3, 2, 1, for example. But these numbers are somehow generic. I mean, so I can also assign 100 to very good, 80 to good, 50 to moderate, like 40 to bad, and so on. So the numbers in this case do not matter much. Another example is the evaluation of students. I can give the grade like excellent, good, satisfactory, and each of these grades can be represented with the number 5, 4, 3, 2, 1. Or if we convert this to the 100 point system, it might be like 100 excellent, 90 points good, like 70 points satisfactory, and so on. And the question is that when we represent these measures in the form of numbers, we cannot. So first of all, these measures are not exact. So what does it mean 100 points? Does this mean that the student who has 100 points is twice better than the student who has 50 points? Well, this is the question. And of course, it's not. So the measures can be ordered. Of course, 100 is greater than 90. And we know that this student is, the evaluation of the student is higher than the student who has 90 points, for example. But we cannot compare them in a way like student A is twice as good as student B. When we measure some physical characteristics like weight, age, time, length, it is possible to compare that something is twice longer, like, I don't know, some I don't know, like this pen is, for example, 3 times shorter than this like small cap of the pen, right? So I can compare them, and it has some meaning. But if we are comparing these kind of variables, it is difficult to say. So someone got like 50 points from statistics, someone got 100 points from statistics. Can I say that the student who has 100 points from statistics is twice better or twice smarter in statistics than the student who has 50 points? It's not possible to claim in this way. And in social science and in the studies of consumer preferences, we have oftenly we have such measures. When we ask people about their satisfaction, when we evaluate something, when we just collect some variables like what is the highest obtained level of education, like bachelor, master, doctoral, and so on. So in many cases we have such variables. And for these particular variables, for this particular type of data, we have to use non-parametric statistical methods, because these variables are, of course, they are not usual variables. In many cases, they are not continuous. And so everything that we have discussed before is not very applicable to such variables. Another case when non-parametric statistics is needed is non-normal distributions. So the standard methodology fails when the underlying assumption of a normal distribution of the population variable fails. For example, t-test. So the t-test is based on the assumption that populations are normally distributed and they have equal variances. Well, okay, we also have a case when variances are not equal, and then we need to compute degrees of freedom in like a specific way, but that was also an approximation. So usually t-test exactly works when variances are equal. And we never know if this assumption holds in a practical situation. So that's a problem. We have some tests. We can apply chi-square test in order to verify normality of the distribution, but we never know for sure that the underlying distribution is normal. And again, in economics, in finance, in social science, oftenly the distributions are not normal. And standard statistical procedures are not applicable in that case. So you are not able to apply t-test, you are not able to apply z-test, and so on. So they are wrong. And in this case, we also can solve this difficulty with the help of non-parametric statistic tests. So you can ask me, well, why have we spent so much time on exploring parametric tests, like everything before, like t-test, z-test, ANOVA, and so on, if they fail in practice? The thing is that parametric tests, everything that we have covered, they are very simple to apply. And in majority of cases, when there are no kind of strong doubts about the assumptions of normality, we are fine with applying those tests. They will work. But sometimes, when samples are small, or when you have enough evidence that the underlying distribution is not normal, it is better to verify your results of the previous tests with also non-normal, non-parametric tests. So what do we mean by non-parametric statistics? Basically, that's the most important question to understand what are we talking about. So what does it mean non-parametric? So let's try to understand the non-parametric statistics from the opposite thing. So from the what is parametric statistics? So everything that I listed in the introduction, t-test, z-test, ANOVA, chi-square test, f-test, and etc. So those are parametric tests. Those are parametric statistics. So parametric methods, they apply to the problems where the distributions from which the samples are taken are specified. So basically everything that we call parametric statistics has an assumption about the underlying distribution. So remember in previous lectures we defined T distribution, Z distribution, chi-square distribution, and so on, starting with the wording. Assume that sample x1, x2, blah 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 is taken from the normal distribution, or has a normal distribution, or something like that. So we started with the assumption about the specific shape of the distribution, of the underlying distribution. And we said that we don't know the values of the parameters of this distribution. So for the normal distribution, we don't know what is mu, what is sigma. So everything that works in this way is called the parametric statistics. For example, in one sample t-test, the population is assumed to be normally distributed, and we don't know mean and variance. So we specify the distribution from which the sample is taken, and the values of mu and sigma squared are not known. So this is the parametric procedure. So parametric means that we don't know the parameters of the distribution, but the distribution itself is specified. We assume that this distribution is normal. So non-parametric methods are applied when the underlying distribution is not specified. We don't care about the distribution from which the sample has been taken at all. So suppose that independent samples are taken from two populations. So you see that we don't specify, we don't assume anything about the underlying distribution. We just know that there are two independent samples that are taken from two populations. And we want, in non-parametric methods, we want to test if the two population distributions are identical. Again, we don't care what is the shape of the distribution. But we want to test this claim if two distributions are identical. We don't explicitly specify the form of the distribution. We don't care about the form. It might be anything. It might be some standard distribution like Poisson, exponential, whatever. It might be some fancy special distribution. Doesn't matter. And this hypothesis that two distributions are identical can be tested with the help of non-parametric methods. We don't specify any parameters. We don't specify mu, we don't specify sigma. We don't care about them. We don't specify the shape of the distribution. So that's why we call such methods non-parametric, because we don't specify the parameters of the distribution and we don't specify the shape of the distribution. And in this lecture, we will talk about one particular example of non-parametric methods, which is called Mann-Whitney U test. So this is a complete analog of two-sample t-test, but two-sample t-test is applied under the assumption of normality, and Mann-Whitney U test is specified without any assumptions of the underlying distributions of two samples. So let's start with the general definition of the problem. So what are we gonna test and how the whole procedure looks like, how the whole problem looks like. It is called a general two-sample shift model. So suppose we have one sample from a population with some distribution function f of x. Look, we don't specify the shape of this distribution. We don't tell that this is normal or something else. We just say that there is some distribution function. We don't know about this function. We know that this sample is taken from this population. And the sample has its own size of n1. And there is another sample, y1 to yn2. So the sample sizes might be different. This is another random sample from the population with another distribution function, g of y. So there are two distribution functions. We don't know their shape, we don't know their parameters, and we don't care about them. We don't care about their shape or parameters. So our goal is to test if the two populations have the same distribution. Formally, we test the null hypothesis that this distribution function equals to this distribution function against the alternative that they are not equal. This is a bit difficult because if we don't specify the actual form of the distribution functions, well, it's hard to compare the whole shape of the distributions. And in most of the cases, we are fine with the following simplification. So you have to understand that this is a simplification of the initial hypothesis. The simplification is y has the same distribution as x, so the shape of two distribution functions are the same, but y is shifted, so the distribution is shifted by some unknown parameter theta, by some unknown amount theta. So what does it mean? It means that the alternative hypothesis says the following: g of y, which is the probability that y is less than some small y, equals to the probability that x is less than or equal to y minus theta, which equals to the distribution function of x evaluated at y minus theta. So look, this is our null hypothesis that two distribution functions are the same, and this is our alternative hypothesis that g of y equals f of y minus theta. So it shifted to the left if theta is positive, or to the right if theta is negative. And basically, this is enough to claim that two distributions are different or same. So here is an illustration of this shift model. This is the distribution function of x. This is the distribution function of y. You see that the shape of the distribution function is just some generic thing. So we don't care about whether it's bell shape or something else. But there is a distance between them, so they don't match exactly. And the distance between their centers is exactly theta. So this is what we test as an alternative hypothesis. Again, instead of testing the hypothesis that two distribution functions are different, because it is hard to test, we test the hypothesis that distribution functions are same but shifted, so they have some distance between their centers, their respective centers. This is something similar to a two-sample t-test, because in the two-sample t-test we are testing the difference between two population means. Now we are testing if there is a difference between two kind of central measures of these distributions, if there is such difference or not. We start the discussion of Mann-Whitney test with the help of Wilcoxon rank sum test. So it was chronologically earlier, and these two tests are connected. So the test has been proposed in 1945, and this test is designed for comparing two populations based on independent random samples. So the idea is the following. So you have to understand the idea, because the idea is simple and the practical implementation is also not that difficult. So we combine all observations in one line. So we have n1 observations from sample 1 and 2 combinations from sample 2. So we combine them together. Then we rank the observations from first to n, from the smallest to the largest. So basically we have to order them, and we have to put the rank to every observation. So this is the first, the smallest one, this is the second, the next smallest, this is the third, and so on, up to n. Now, what we have to do if there are two or more equal or tied observations. So for example, we have 3 and 3, two numbers that are equal. So we have to assign the average of their ranks. So for example, we have like 10, 12, 15, 15, 16, right? So 10 is the first, 12 is the second, and then you have 15, 15, which is third and fourth. But instead of third and fourth, you have to assign 3.5, 3.5 to the next two numbers. And then 16 goes on the fifth place, and so on. And the idea is, if the two populations are identical, the rank sums should be proportional to the sample size, n1 and n2. So the idea is simple, because if two distributions are identical, then when you order the observations from these distributions in ascending order, there should be like the first one should be from the first sample, the second from the second sample, the third is also from the first sample, the fourth is from the second sample, and so on. So there should be some kind of switch of the ranks from the first to the second, and so on. So the rank sums should be more or less equal. or proportional to the sample sizes if the sample sizes are different. So for example, if n1 and n2 are equal, the rank sums are going to be nearly equal. And if the observations in one population tend to be larger, so if there is a shift between the two distributions, for example, sample 1 would have larger rank sum. And in this case, this is going to be the enough evidence to claim that the distributions are not identical. If one rank sum is very large and the other is very small, it may indicate that there is a statistically significant difference between the locations of the two populations. Again, going back to this picture, if I'm taking some sample from this distribution and from this distribution, you see that from the right-hand side distribution, I will always have larger numbers than from the left-hand side distribution. So the rank sum of y is going to be larger than the rank sum of x. So that's exactly the idea of Wilcoxon rank sum test. So let's see an example, a very simple example how this test can be conducted. Suppose that there is a telecom operator and this telecom operator raised the tariffs to the chosen group of customers. And we take the sample 1 from this group of customers who were treated by the increased tariffs. And we measure the number of calls they made over the last month. So how many times have they called during the month? For the other group of customers, sample 2, the old tariffs were kept, so nothing has changed. And from each group, 4 observations were taken at random. And this is the data. So we have group 1, and the number of calls here is 27, 31, 26, and 25. And the group 2, 32, 29, 35, 28. So the question is, do we have enough evidence to claim that the locations of the population distributions in group 1 and group 2 are different? So basically, this distribution, the underlying distribution of group 1, differs from the underlying distribution of group 2. What is the practical use of this? Well, we can claim that the raise in tariffs negatively affects the activity of our customers, for instance. And if it negatively affects the activity of our customers, so probably we earn less. So remember microeconomics. In microeconomics, you have heard, I hope, and remember about elasticity of demand. When you raise prices, quantity demanded goes down, and it may affect your revenue. If the demand is elastic, it affects your revenue negatively. If the demand is not elastic, it affects your revenue positively. So the same thing can be applied here. If we find that the group 2 and group 1 differ in their distributions, and specifically the group 1 distribution is smaller than the group 2 distribution, so it is shifted to the left, well, we may claim that the demand is elastic and raising tariffs negatively affected our revenue. Might be like this. So what we have to do in order to apply the previously discussed Wilcoxon rank sum test? First of all, we have to put all observations in ascending order and assign their rank. Here, I just mixed everything and put the numbers in the ascending orders. With the bold, I marked the observations from the first group, and with the usual font, there are the observations from the second group. And look, here is the red. 1, 2, 3, 4, 5, 6, 7, 8. So what is the position of every number in this ascending ordered string of numbers. Now, the rank sum for the group 1. I'm taking these ranks 1, 2, 3, 6, and I sum these numbers 12. The rank sum for the group 2 is 4 plus 5 plus 7 plus 8, which is 24. Now, let's try to look at this table and understand the idea of Wilcoxon test. Look, 3 observations are located to the left of the rest of the observations, right? So these observations are located somehow to the right, the observations of the second group, and these observations of the first group are located to the left, except for this one. 31 is somehow in the middle. And the limiting case is when the group 1 would have 1, 2, 3, and 4 ranks, and the sum is going to be 10 in this case. So this is the smallest rank sum, smallest possible rank sum in this case. The largest possible rank sum is 5 plus 6 plus 7 plus 8, which is 5 plus 6, 11, plus 7, 18, plus 8, 26. The largest possible rank sum is 26. And of course, if you have this largest and smallest possible rank sums, then it would have enough evidence to claim that two distributions are not equal. As a test statistic for Wilcoxon test, we are taking the rank sum for the first group, for the smallest group usually. Now, for every test, we should have the critical or rejection region. But what we have to do, we don't know the distribution, so we don't know what is the distribution of this W, of this statistic. Basically, it is possible to compute based on counting, based on the probability theory, but I don't want to discuss it here. If you need, you can, for example, Google it. So last time, in one of the lectures, Valeria asked me about using tables. So basically, the same is here. So we can ask for the critical values. Yeah, so here I was asking for Wilcoxon rank sum test. Not in Python, just as usual. And yeah, so we can get it from somewhere. Here we have the table of the critical values. For two-tailed test, when alpha is 5%, we can take, and here M and N represent the size of each sample. So basically we are looking for 4 and 4. And this W is 10 and 26. So these are two, like, left and right border of the critical region for the W statistic. So which means that the rejection region consists of two numbers, if W is 10 or if W is 26. In this case, we reject the null hypothesis. In our case, W is 12. So on the 5% significance level, we do not reject H null, and we cannot claim that two populations are different. So we claim that two population distributions are equal. Look, we don't employ any parametric assumption. Nothing has been said about normality. Nothing has been said about any other assumptions, even about the parameters of the distribution. We don't compute anything like average or median or whatever. We just order the numbers, and with the help of their order, we come to the conclusion that there is not enough evidence to claim that the distributions are different. But there is an extension of Wilcoxon test. And so the most popular test that does the same, that solves the same task, is called Mann-Whitney U test. So basically they have the same result. But, well, in practice, Mann-Whitney, or sometimes it is called Mann-Whitney Wilcoxon test, like with three names, it has been proposed 2 years later, in 1947. And they are connected to each other. You will see that these two tests are related. And when we want to compute U statistic for Mann-Whitney test, we have to compute W statistic from the Wilcoxon test. So they are related. But the initial idea has been different, slightly different. So we obtain this U statistic as following. So again, the first step is the same. We order all observations according to their magnitude from smallest to largest. Then we count the number of observations in sample 1 that precede each observation in sample 2. So you will see an example. What does it mean? So basically we take observations of sample 2 and look how many observations from the sample 1 are before. And then we sum the counts from the second step. And this is going to be the statistic U. The logic is that very large or very small values of U provide sufficient evidence that there exists the difference between the distributions of populations 1 and 2. So let's see on our example how the U statistic works. Again, I order all my observations. I put all my observations in one row. But now I specifically label from which sample the observation comes and what is the position of this observation. So this is the first smallest value from the first sample, from the sample X. This is the second observation from the sample X. This is the third. And then I have the first observation of sample Y, second observation of the sample Y, then I have fourth observation of sample X, and third and fourth of observations of sample Y. And now I do the following. I'm taking the first observation of the sample Y, and I compute how many observations from sample X are before. So they are located to the left. There are 3. Like this. The smallest observation of Y is 28. Now, there are 3 observations of X that precede this first observation of Y. So to the left of Y, I have 3 observations of X. 1, 2, 3. So U1 is 3. So the first count is 3. Now I move to the next observation of Y, which is 29. And again, to the left of 29, I see 3 observations of X. So there are 3 observations of X that precede this next observation of Y. Now, the third observation of Y has 4 observations of X before. And the same for the fourth observation of Y. Again, fourth observation of Y has 4 observations of X before. So U3 and U4 are 4 and 4. And now U statistic is computed as the sum of these 3, 3, 4, and 4 of these elements. So this is my U statistic. For U statistic, it is possible to find also the critical values. For instance, in the book of Wackerly that you use on your exercise sessions, there is a table. There is a table here, distribution function of U. So the table is slightly different to understand, but basically you have to do the following. You have to find the table where n2 equals to the number of observations in the second sample. So in our case, n2 is 4. And then you have to look for n1, which is also 4 here. So now, here we have probabilities. And here we have the values of U. We are working with a two-sided test. So which means that the probability function should be approximately 2.5%. So the closest value to 2.5% is this one, 0.0286. And the U statistic is 1. So if U statistic is 1 or less than 1, then I reject the null hypothesis. But this is the left tail. The right tail is obtained in the following way. So the right tail is 16 minus 1. So 16 is 4 times 4. So the size of first sample multiplied by the size of the second sample. And it is 15. So my rejection region is either U is less than or equal to 1, or U is greater than or equal to 15. In our case, test statistic is 14, which does not belong to the rejection region, and we do not reject H null, and we cannot claim that two population distributions are different. So we claim that they are equal. We see that the result of Mann-Whitney test is exactly the same as the result of Wilcoxon rank sum test. You see that manually Mann-Whitney test is not that nice to implement, because you have to order the observations, you have to count how many observations of one sample are preceding the observation of the second sample, and so on. I can show you how we can apply the same in Python. Basically, there is a specific function that helps us to implement this Mann-Whitney test. So what we have to do? We have to import NumPy library, and we have to import from SciPy import stats. The familiar library stats from, like, model stats from the library SciPy. Now we create two samples. So sample 1 is NumPy array of these observations. Let's go back to the initial example here: 27, 31, 26, 25. 27, 31, 1, 26, 25. And sample 2 is 32, 29, 35, and 28. Now in the module stats, we have the function which is called Mann-Whitney U. Basically, if you want to know how it works, you can ask the help. But the simplest way is to provide X and Y, so sample 1 and sample 2. Sample 1, sample 2. We can specify the alternative if needed, but by default we have the two-sided alternative. And so we can specify also the method, and method Well, in our case, it's gonna be automatic by default, but we can also specify that this is gonna be an exact method. So let's see how later we will talk about the asymptotic method as well. And that's all. We run the test and we see that there is a result consists of two values. So there is statistic, which is 2, and which is not the same as we have this computed here, because we computed U statistic to be 14. So now we will try to understand why the statistic is different. And p-value. And you know from parametric statistics that p-value is very nice to interpret, because we look at the p-value, and if p-value is greater than 5%, we cannot reject the null hypothesis at 5% level of significance. Basically, that's all. So now the question is, why do we have different result of the statistic? Well, if we switch the order of samples in our function and put sample 2 on the first place and sample 1 on the second place, you will see that the result of the statistic is exactly as we have, 14. Because in the first try here, it compares how many observations of sample 2 are before the observations of the sample 1. So the reverse task. So basically, how to get 2? We have to look how many y's are before this, 0. How many y's are before this, 0. How many y's are before this, also 0. Then we skip this, and how many y's are before this x, 2, 1 and 2. So U statistic is 2. Instead of counting how many x's are before each y. In this case, it's going to be 14. Well, this is how you can implement Mann-Whitney tests in Python, no matter how large is your sample. So now it is going to be very, very simple, just one line. And with one line, you have the result of this test. Well, basically, we can try also. There should be some t-test, I guess. Yeah. If you put here the t-test, look, for the t-test, we have, well, almost the same result if we use t-test from the parametric statistics. But don't be confused with this that the result is the same or like nearly the same. In some cases, the results may differ. So this is just a particular example when t-test, parametric t-test, yields almost the same conclusion as the non-parametric Mann-Whitney test. Still, Mann-Whitney test is more robust to the cases when the normality of the data is questioned. Okay, so now just to wrap up the general approach in Mann-Whitney test. So I gave you an example. Now, in general, what we have to do. So first of all, the first population is always the population where the smaller sample is taken. So we have to compare the sizes of the sample. If they are not equal, population 1 is the population from which the smaller sample is taken. Now, the null hypothesis says that the distributions of populations 1 and 2 are identical. The alternative hypothesis can take 3 different forms, as it was in our 2-sample t-tests before. First version, the distributions have different locations. Distributions have different locations. This is going to be 2-tailed test. Another alternative, the distribution of population 1 is shifted to the right of the distribution of population 2. This is going to be right tail alternative. And the distribution of population 1 is shifted to the left of the distribution of population 2. This is going to be the left-tailed alternative. The test statistic can be computed instead of counting how many observations of X precede each Y, the test statistic can be computed in the following way. You see here we have W, and W here is exactly Wilcoxon rank sum that we have counted initially. But here we have also N1 and 2, the product of them, plus this fraction N1 times N1 plus 1 over 2. So basically we can check that this holds. Look, what was the W from Wilcoxon test? Here. The W was 12, the rank sum for the group 1. Okay, so W is 12. Here we have N1, 4 times N1 also 4, so which is 16. 16 here. And here we have 4 times 5 over 2. 4 times 5 is 20, over 2 is 10. So 16 plus 10, which is 26, minus 12. 26 minus 12 is 14. And this 14 exactly matches what we have computed here, but in more concise way. And rejection region. Depending on the alternative, rejection region either values of u that are less than u0 or values of u that are greater than n1 and 2 minus u0, where this u0 is taken from the table as I showed you. So we have to take such u0 that the distribution function equals to alpha over 2. Here, for example, if we tested two-sided alternative and alpha was taken as 5%, 5 over 2 is 2.5. We are looking for the closest value of probability here, which is 286, and u0 is 1. So that's how we got the rejection region on the previous slide, which was u is less than 1 and u is greater than 15, because it was 16 minus 1, exactly 15. This is for the two-tailed test. For the left-tailed test, we have to take u0 such that the whole probability equals to alpha. So in our case, we would take, if we want to test the left-tailed alternative, we would take u0 equals to 2, because probability is almost 5% here. In the right tail test, we take n1 and 2 minus u0, and again u0 is such that it provides us the probability equal to alpha. So basically this is all about Mann-Whitney test, and there is only one last step. As usual, there is a simplification of this test. If we have samples that are larger than 10, so both samples should be larger than 10, we can apply the simplified test. The simplified test has the following idea. If the population distributions are identical, so which means that null hypothesis is true, the U statistic has the following expected value. Expected value is n1 and 2 over 2. And the following variance, n1 and 2 times n1 plus n2 plus 1 over 12. So again, we don't derive these variances, just we believe to the textbooks. And when the samples are larger than 10, then the following familiar to us Z statistic has approximately standard normal distribution. So that statistic is u minus expected value of u over the square root of variance of u. This is the standardized variable familiar from the previous course of statistics, and it has a standard normal distribution. And basically, this is the test statistic now. I just plug expected value of u here and variance of u here. I have my z statistic here. And the rejection region is constructed in the same way as the usual z-test. For the upper tail critical region, z should be greater than 1 minus alpha quantile of standard normal distribution. For the lower tail alternative, z should be less than alpha quantile of the standard normal distribution. And for two-tailed alternative, the absolute value of z should exceed 1 minus alpha over 2 quantile of the standard normal distribution. Again, you are able to apply this approximation and simplification only when the sample sizes are greater than 10. So both samples are greater than 10. In this case, that statistic is going to be like this. And in Python, you can implement this simplification exactly with choosing the method instead of exact. You choose asymptotic. And you see that, well, that statistic is the same, but p-value is slightly smaller than p-value here in the exact test. Well, but basically we are not able to apply this z-test here because the samples are less than 10. Any questions about Mann-Whitney test? So in practical applications, it is usually recommended to apply Mann-Whitney test instead of t-test for sample means. Because as I said, Mann-Whitney test being non-parametric statistics, first, it is able to be applied to the ordered measures that we have discussed initially when you, for example, want to compare the consumer taste test or consumer preferences, their evaluations of your service and so on. And second, it is also able to deal with the problem of non-normal data because it doesn't take into account any parametric assumptions of the underlying random variables. There is a non-parametric analog of ANOVA, which is called Kruskal-Wallis test. I'm not going to cover this, but if you are interested, you can also study this yourself. Basically, there is similar. So let's, again, in Python, for example, just you have to understand the logic. Let's create sample number 3, which is going to be NumPy array. Let's take some other values, 34, 38, 37, 35, let's say. And then in stats, there is this Kruskal function, which is the Kruskal-Wallis h-test for independent samples. So we have to provide the samples as an argument, and basically that's all. So we do the following. Sample 1, sample 2, sample 3. When I run this, you see that, well, it compares in the same fashion the distributions of 3 groups. Now, it compares the 3 distributions, and being, so p-value being less than 5%, says that the distributions are different because I specifically made this distribution well, different from the previous two distributions. For example, if I put here some values that are closer to the to previous distributions like this, you will see that the Kruskal test will have p-value which is greater than 5%, and it will say that these samples, like these two samples and this third sample, have similar underlying distributions. So same idea, different implementation, of course, because Kruskal-Wallis test has a different statistic, and well, this is just for your information that there is a non-parametric analog of ANOVA, which you can also apply in the case of comparing ordered variables or in the case when non-normality is present. Yeah, so this is what I said. You have to apply non-parametric tests when the assumption of normality is questioned. Yeah, and basically this is all about the non-parametric statistics, so the rest is gonna be just our organizational questions. Let me remind you that there is a home assignment number 8 till next Wednesday. The final exam is gonna be conducted by Klim, so discuss the details with him tomorrow on the exercise session. I will pass all your preliminary results to you via Moodle and to him. So he will know your grades from home assignments and he will know your grades from the midterms. We are not departing, and we keep meeting each other every week. But now from the next week, be careful. We meet on Wednesdays only for the econometrics course. So same time, the link for the meeting is gonna be different. I will provide you with the new link. So also this is very important thing. So this link will finish working today. And yes, we will have 8 or 9 weeks, I don't remember exactly, of econometrics course starting the next week. Questions? Well, okay, then congratulations. Our mathematical statistics course is over. So you still have something to do. Exercise session tomorrow, home assignment till the next week. Then we compute the results and proceed with the next subject in the sequence. Thanks for your attention. Have a nice day and see you next Wednesday.